we'll continue with the next step, that is check for effective depth required. Okay, so for that we're going to equate mu is equal to mu. So whatever the mu you have calculated, this is equal to, for Fe415 grade steel, mu limit is equal to 0.138 FCK BD square. So from this you can find out D. This is the D required to take as bending moment. So this is 69.73 mm. Okay, means to take that bending moment 13.42 into 10 raised to 6 kilonewton meter, how much depth is required? 69.73 mm. But actually how much we are providing? We are providing 116. So anyhow this is greater than what is actually required, hence it is safe. Okay, so next move on to the step, that is the area of main steel, that is AST we are going to find out. As usual, we are going to use the formula. First find out the percentage required, that is the PT is equal to 50 into bracket 1 minus under the root of 1 minus 4.6 mu upon FCK BD square whole divided by Fy upon FCK. So again important thing is substitute mu, that is 13.42 into 10 raised to 6. And B, whatever this B is there, width of slab, that is 1 meter or 1000 mm, you have to substitute for B. Okay, so after substituting all the values, we will get a percentage of steel, that is 0.29%. Okay, so PT is equal to 0.29%. So once if you get the percentage, then calculate the area of main steel. So therefore, area of main steel AST is equal to percentage, that is PT divided by 100 into B into small d, remember B into D. So 0.29 PT divided by 100, B is 1000 mm, D is effective depth 160. So area of steel required is how much? 339.88 mm square. Okay, now here as in the beginning we have assumed 8 mm diameter bars. Okay, for the main steel. So for this 8 mm diameter, what will be the spacing? Remember, once again I am repeating here, in slab don't find out number of bars. Okay, so we are designing 1 meter width of slab. So instead of calculating number of bars, you have to calculate spacing. Okay, spacing of these 8 mm diameter for 1 meter steel. So spacing of main steel is equal to, now it is reverse. Okay, so area of 1 bar divided by total AST. Okay, so when you are calculating number of bars, it is total AST divided by area of 1 bar into 100. But here it is area of 1 bar divided by total AST into 1000. Why this 1000? So this spacing will be for 1 meter width. So that's why I am multiplying 1000. So we are assuming 8 mm diameter, that is pi by 4 8 square divided by this total AST 339.88 into 1000. So this is spacing comes out as 147.89 mm. So this is rounded off to lower value. Remember, don't provide 150 mm. So lower value you have to round off. So finally you can say that main steel, that is provide 8 mm diameter bars at 150 mm center to center as main steel along shorter span. Okay, at the bottom, right, along the shorter span, we have to provide 8 mm diameter bars at spacing of 140 mm center to center. Okay, so this is main steel. Okay, next up, we will check for the shear stress, whether really the stirrups are required in this slab or not. We are going to check. So, what percentage of steel we are available at the support now? Okay, so PT is equal to AST upon BD into 100. Okay, so AST upon BD into 100. So this is the percentage of steel available at support. Now see here, PT is equal to, percentage is equal to AST. So what is AST? Total AST is 339.88. Okay, so 339.88. So I have multiplied 0.5. Means at support, not all this steel is available. Okay, at support only 50% steel is available, because I tell this, so why I have multiplied this 0.5. Okay, so right now 0.5 into AST, this AST, right, divided by B into D into 100. Okay, so this percentage of steel available at the support is 0.146. Okay, 0.146 percentage of steel is available. Now, for this steel, right now let us calculate the nominal shear stress tau v. Okay, so shear stress is equal to force divided by area. So that is Bu by B into D. So shear force 16.59 into 10 to the power of 3 Newton divided by B is 1000 into 116 effective depth of the slab. So nominal shear stress comes out as 0.143 Newton per mm square. Okay, now design shear strength. Okay, go to the table number 19. Table number 19, IS 456 2000. Okay, so from that table we are going to get the tau c value. So tau c value for this percentage of steel. So here in this case we are going to get 0.30 Newton per mm square for tau c, that is maximum design shear strength of the concrete. Now in slab this tau c should be multiplied with K value. Okay, tau c value should be multiplied with K value. Now where are we going to get this K value? So this K value we are going to get from the page number 84. Okay, so I think it is table number 27. So table number 27, page number 84 of IS 456 2000. So if you go to this page number 84 and table number 27, first there you have to see what is the slab thickness. This is the overall depth. Capital D is 135 mm. So for this total depth of slab, what will be the K value? So K value is equal to 1.30. Okay. Now whatever tau c you have calculated, multiply that tau c with this K value. So therefore K into tau c, that is 1.3 into 0.3. So we get this term. This is the allowable shear strength of concrete. Okay. So this K into tau c is 0.39. Now compare this and tau v value now. Okay. Tau v is compared with tau c. If tau v is less than K into tau c, okay, tau v is less than K into tau c, no shear reinforcements are required. Okay, so in most of the cases, right, in slab always this check will be not necessary, but you have to, as per the code, you have to check. So you cannot see the shear reinforcement in slab. Okay, so always this check will be satisfied. Now anyhow, so this tau v is 0.143 is less than K into tau c, that is 0.39. So shear reinforcements are not required. Okay, so this is one of the important step you have to remember. So once this check is over, now the next check is check for development, that is deflection control. Okay, so whether whatever the reinforcement we have provided or whatever the dimension we have provided, whether these are sufficient to take the deflection, that we are going to check. So as usual, same procedure we are going to follow. First L by D maximum is equal to L by D basic into KT value into KC value into KF value. Okay, so L by D maximum is equal to L by D basic. It is 20 for simply supported beam slab. It is 20. So 20 into KT. So where are you going to get this KT value? KT value you are going to get from figure number 5. Okay, figure number 5 from IS 456 2000. So KT is 1.4. Then KC is not doubly reinforced. So this automatically this is 1. And for this is not T beam or a slab, it is 1. So KC and KF are 1. So KT you have to calculate 1.4. So this L by D maximum we are going to get 29. Okay. Now actually how much we are providing L by D? So L by D actually is equal to L. What is L now? Effective short span. LX. What I can say that LX. Effective short span. That is 3.116. Already we have calculated effective span LX. So that you have to take here. So L divided by D. Effective depth 116. So how much you have got actually? It is 26.8. So compare this L by D actual with L by D maximum. So this L by D actual is less than L by D maximum, then automatically the deflection are within the permissible limit. So then there is no necessity of revising the depth. If L by D actually is more than L by D maximum, then again you have to go back to the first step and repeat all these steps. Okay, so normally it will going to be satisfied. So hence deflections are within control. And next is distribution steel. As we have seen in slab, main bars are provided along the shorter span. Okay, over that main bars perpendicular direction, distribution steel is provided. So distribution steel we are going to calculate AST D. D indicates distribution steel. So how to calculate this area of distribution steel? So area of distribution steel 0.12% of gross area. Okay, 0.12% of gross area. This is for Fe415 grade steel. Suppose if you are using Fe415 grade steel for distribution steel, then it is 0.12% of B into capital D. Suppose if I am going for Fe250 grade, then this area of distribution steel will be 0.15% of B into D. Remember, if you are going for Fe415, it is 0.12% of B into D. If you are going for Fe250 grade steel, it is 0.15% of B into D. So 0.12 divided by 100 into B is 1000 mm, D is overall depth of the slab is 135. So total area of distribution steel is required 162 mm square. Okay, then last you can write down. For this also you can assume 6 mm or 8 mm diameter steel. So providing 8 mm diameter at 300 mm center to center as a distribution steel. Okay, how about this 300 mm? Again same thing. Now you have to find out the spacing for this distribution steel. That is area of one bar, that is pi by 4, 8 square divided by total AST 162 into 1000 for 1 meter. So we will get this 300 mm center to center. So after calculating all this main reinforcement, distribution, then check for shear, then check for deflection, last whatever the calculation you have done, that you have to show in the form of sketch. So this is the last step. We are going to draw the two sketches. One is a plan and another will be cross section. Now see, first if you see this in to in dimension is 3 meter. This is given room dimension. Then width of support. This is width of support 230 mm. So over this the slab will be resting. So this is the overall depth of the slab 135 mm. And whatever you are seeing, this is the main steel. Okay, main steel. What is that main steel? See, 8 mm diameter at 140 mm center to center is provided at the bottom. Okay, and whatever you are seeing, these dots. Okay, these dots are distribution steel. What you have calculated here? Distribution steel, that is 8 mm diameter at 300 mm center to center. Distribution steel. One thing I wanted to tell you here is whatever this main steel you have provided, okay, can you see these? It is bent and taken at the top. Why this is required here? Now, in the simply supported either beam or slab, if you consider, where is the maximum bending moment? Maximum bending moment will be at the center of the beam. And as you go towards support, what is bending moment? Bending moment is 0. Okay, so there is no full reinforcement is required actually. So what we are going to do? Near the supports, we are going to bend the main steel and taken at the top. So these bent and taken top, these bars are going to act as a shear reinforcement. They are going to act as a shear reinforcement. They are going to take the shear stresses. So near the supports, right? Alternate bars. Okay, all the bars are not bent and taken. Alternate bars. So one bar, okay, you can take straight, and next bar you can bend. Next again one next bar, take from support to support straight, then next bar you can bend at the support. So like this alternate bars are bent and taken at the top. So this is cross section. This is a plan. See here. Now see this main bar. Okay, if you cut the slab horizontally, and if you see from the top, what are you going to see? You are going to see this. So one bar, right? It is bent this side, this near this support, and next bar it is bent at this support. Okay, so alternate bars are bent and they are taken at the top. So this is the plan, and perpendicular to this direction. So this is LX. Okay, this is LX and this is L1. So over these main bars, these are the distribution bars. Whatever you are seeing, these dot lines, okay, are the distribution bars. Okay, so this is the plan at the bottom. This is the plan at the bottom, and this is the cross section of the slab. Okay, so these are the steps you have to remember. First you have to find out the dimension, that is using L by D ratio. Okay, next step is you have to, once if you are finding out the dimensions, the next will be, okay, you have to calculate the total load. Okay, then you have to calculate the effective span, right? So once if you find out the effective span, then you can check for the next calculate the bending moment and shear force. That is total load, you have to calculate W. Then using total load, you have to calculate the maximum bending moment and maximum shear force. Then check for the effective depth. Calculate area of main steel, that is AST. Okay. Then check for nominal shear stress. Check for the deflection. Then find out the area of distribution steel. And finally, you are going to draw the sketch showing the details of reinforcement. So these are the steps to be followed. So design of beam as well as design of one-way slab is almost same. Okay, there is no much difference. Only thing, wherever the B is there, you have to take here 1 meter or 1000 mm. So hope you have understood this problem. Okay, if any doubts, you feel free to ask me. Okay, so in the next class we come up with one more problem. Okay, so thank you very much for attending this session. Have a nice day.